Oh, it's indeed, it's starting this automatic transcription part, yeah. Okay, so, but that also means that you can hear me, or everyone can hear me then, I guess.
All right. Yes.
Okay, yeah. Okay, so the point of the probabilistic programming lectures is to interleave the theory lectures with points where you get a chance to try out certain things. Bayesian machine learning, especially in the early phases when you're still working on probability theory, can be a bit abstract, can be a bit mathematical. But in the end, we are doing computations to obtain parameter estimates or predictions of some variable that are going to be used in an engineering application. And so these probabilistic programming sessions try to form this bridge between the theory lectures and how do I solve a problem? How do I apply these techniques to obtain parameter estimates for a particular problem, a particular application? So there'll be 4 probabilistic programming sessions. They're interleaved with various sections of the rest of the course. So this first probabilistic programming session will be just on what is a prior, what is a likelihood function, what is a posterior, how do you do model comparison. It'll be so in the remainder of the probabilistic programming course, we'll be using a few software packages where you can specify a probabilistic model, and then under the hood, it's doing some form of automatic inference. This first session will just be purely on using parametric distributions. We won't go into using a probabilistic programming software package yet. The other probabilistic programming sessions we will. And we'll start out with very simple problem settings. There's a questionnaire in the probabilistic programming 2 that looks at very simple models, the beta Bernoulli, the Dirichlet categorical, and the Gaussian likelihood. The probabilistic programming 3 will be looking at a classification and a regression setting. Both will have sort of a real-world application. One is on the stock market, and the other is on. I actually forgot. But it's at least last year's feedback from students was that it was very pleasant to have sort of a real-world, concrete example where we are applying these techniques. And the final probabilistic programming session will be on dynamic models and the latent variable model. So we'll use a Gaussian mixture model there to cluster some scientific findings in archaeology, and dynamic model will have a look at tracking a cart on a rail going up a mountain. So again, the point of these sessions is to bridge this gap between theory and real life applications, real problems. And so if you have any questions on how do I make this step, how do I bridge this gap between theory and application, this is really the time to ask that. The probabilistic programming sessions will be in the programming language Julia. Julia is quite similar to MATLAB and Python. Throughout this course, we'll mostly use code that very much resembles Python and MATLAB. Julia has a few more advanced features that we'll simply not use during this course. We don't explicitly teach you Julia, but most of the cells in the earlier probabilistic programming sessions, if they contain a piece of code that is somehow different from Python or MATLAB, I'll have a code note explaining what is exactly happening. And so here, for instance, in MATLAB, in Python, you would have an import functions. You would import a module, and you can import specific functions or submodules from a module. In Julia, there is a import function, but we tend to use this using reserved keyword. So now I am using the software package or the module PKG, which stands for package, and package is a package manager. And so this particular using package that activate workspace, package that instantiate, this is going to automatically install all of the dependencies that you'll need, all of the software packages that you'll need for the course. So you're going to need stuff on parametric probability distributions, plotting, how to read data files, and some of the probabilistic programming software packages themselves. You'll be using Fornilab, which is one of the packages. And so if this cell runs, you'll see it'll report all of the packages that it's installing, and each of the packages is their own dependencies. If that all goes well, that means that your entire environment is set up to be able to run all of the code during the probabilistic programming sessions. Yeah, so if there are specific questions on, so why is Julia like this, or how do I do something in Julia, or why are you using Julia at all, please do ask. We have and we have good reasons for all of these things. If you're interested in learning a bit more about Julia, and you already have some experience in MATLAB and Python, I do recommend this link. It's a long list of noteworthy differences from other languages. So there's MATLAB, Python, C, R, and Lisp. Not sure how many people are familiar with Lisp, but so it has very detailed things like Julia is not copied when assigned to another variable. A is B just means that you if you change the elements of B, then you'll modify A as well. So A is just another pointer to the matrix stored in memory that's already called B. Whereas in MATLAB, you would automatically copy that sort of subtle behavior that it's good to be aware of those things. But in general, you won't need this information to understand what is happening in these cell nodes. But if you're interested, it's there. Also, there's a really great intro to programming in Julia. It's a video presentation. It's a bit long, but it's also entertaining, so it should be fun. Are there already some questions at this point? Yeah, Jeet Bala. Can we know your first name? Actually, you're in the list as Jeet Bala, but other people have shown us with their first names. That helps.
Yeah, sure. My name is Gautam.
Gautam.
Yes.
Okay. Yeah, I remember that. Gautam. Yep.
Yeah. So I just had one question. So while I was going through the video tutorial of the corresponding lecture, so there was one point where we when we define the likelihood function, we see that the values are pretty yeah. So yeah, down. Yeah. So here when we look at the plot, it's actually the values are pretty weird. So you mentioned that it's actually not a valid PDF because we are actually basing this out of the data. So I was just a bit confused there. So I tried to see if the integral of that would, some integration of that would go to 1, but I couldn't find like proper code to do that. But I just want to understand whether does that integral sum to 1, or is it not even a valid PDF? And if not, then like, isn't it violating, the probability theory calculus concept when we actually apply Bayes formula in the next step? But yeah.
Well, this is an excellent question, and I thank you very much for asking this question, because that means we can spend some time on this. It is indeed not a proper probability density function. It's not a probability distribution, and that is because the likelihood is a let me just go up here. Yeah, so in this part, the model specification, we're also just talking about the likelihood a little bit, but So what you can see here is that the likelihood of the data in its entirety, given some parameter, in this case we have IAD data, so independently sampled observations. That means that we have a product over these individual likelihoods. And what you'll see here is that, so we have some x, and this p is a, or in this notation, it's a distribution of x and theta, or it's conditioned on theta. But x here is observed. It's not an unknown random variable. It's a known value because we have observed it. Theta, on the other hand, is not set by us. We haven't fixed or clamped or set theta to some value. We're not looking at the probability of encountering a certain data point given a particular value of the parameter. No, this is really this p. It's very tempting to view it as a probability distribution, but what it's actually doing is it's telling us something about what values of theta are likely given these observed values for x. And you can see that described a bit in this particular example. Suppose these first two participants have correctly guessed a beverage and the third one has incorrectly guessed it. So that means we have three observations, 1, 1, and 0. So this D is a data set of 1, 1, 0. And so if I try the value of theta at 0.8, so I can do that and I can evaluate this likelihood function, P, then I get 0.8 times 0.8 times 0.2, and that gives me a number under the likelihood function. And then I try a different value for theta, so perhaps theta is 0.4, that gives me a different number. Then I try another value for theta, and that also gives me a different number. So what this likelihood function is doing is saying, so given these observations of x, how likely are each of these values of theta? And so more likely values have higher numbers. So here, this might be a better example. So this particular value of theta is the most likely one. And so here, basically what I've done here is I've taken this particular example here, and I've just ran a range of theta values and then evaluated the likelihood function for all of these observations in this experiment, and then plotted the likelihood of each of these values. But so the reason that this is so low, this y-scale, called 10 to the power minus 15, is because under a Bernoulli distribution, yeah, so these probabilities are all, in the individual probabilities of these likelihoods are all numbers between 0 and 1. Mm-hmm. But we are multiplying each of them. And so we're multiplying over n times, so we're multiplying these numbers that are between 0 and 1 with another number between 0 and 1, so the result of that will always be smaller. And yeah, so we keep doing this. And in this full data set, there are, I forgot how many, I think 50. 42 plus 15, so yeah, that's 56. So we're multiplying 56 numbers that are smaller than, or that are between 0 and 1. And that'll just give you a very small number. And that's why this y-axis is of this particular scale. Yeah, so Bayes' rule applies to probability distributions, but in this particular instance of estimating parameters based on data, it's good to know that one of these random variables here is observed. And that means that this thing will not integrate to 1. You're multiplying with p of theta, so the result will also not integrate to 1, but that's why you're also normalizing it again with p of d, the probability of the data set. And the result after renormalization will be a valid probability distribution. This thing, posterior, will be a valid probability distribution. Does that answer your question?
Yes. Yeah, that does. Yeah. Okay. Yes. Mm-hmm.
So that's why it's also important to have this evidence term.
Okay.
So in very complex models, so you can, for instance, build Bayesian neural networks. Then you can have this like a really complex likelihood function, something that is not, that's not just the product of two exponentials, or well, theta to the power x and 1 minus theta to the power 1 minus x, but it can be like a full neural network or something really complicated. And that's fine, because in the end it should be a function that indicates that certain parameters, it should be informative of the parameters given data. So it should have something, should have a shape that looks like roughly like this. That's all fine, as long as you can renormalize. And this is typically where research in Bayesian inference, Bayesian machine learning takes place. Can we develop technique, because computing this evidence term P of D is difficult, involves intractable integrals, and can we then design methods that still allow us to do this, still get posterior distributions out. And we'll treat this later in the course. Not neural networks, but free energy minimization, which is a technique to obtain posteriors.
Got it. Yeah, okay, thank you so much.
Yep. Cecile, you also have a question?
Yeah, it was more a practical question, because I was wondering, like I created my own notebook, like to redo the exercise, but then I had to add all the packages by hand.
Yeah, so what you can do is, so what we're doing here in this cell is that we're pointing to a particular folder. So in, let me just, let's see. So this is the Github repository. So this is where we're really taking a software development approach to developing this course. You go to lessons, notebooks, and then specifically PropProg. You'll see here the 5 probabilistic programming notebooks, and workspace is a folder. This folder contains 2 files, project.toml and manifest.toml. If you copy this folder, so suppose if you're working if you're working in a notebook somewhere else in either this hierarchy or someone else on your computer, if you copy this folder and put it in the same directory as the notebook that you're working on, then you can use this cell, you can use these 3 commands to call that workspace, and it will set up a virtual environment where you have access to all of these packages. And then you're able to run them there.
Yeah, okay, thank you.
Yeah, maybe just as just give a bit more context. If you look at project.toml, this is really just a list of which packages we need for the course. They're given a code. This is just a unique identifier. And then if for any package we need a specific version, then it's listed here on the compat, cc, blah, blah, blah. And this Julia package PKG, it generates a manifest. So it says here this file is machine generated, and it just says, okay, I need all of these packages and then these specific versions of these packages, and this is how they're linked. For instance, this particular package has somewhat dependent as these dependencies. This is why we often have to run that package.resolve function. Resolve just means that package will start to adjust this manifest file to ensure that all of these different software packages that we're working with play nicely together.
Yeah. Okay, thank you.
Yep. Let's see. So Rong asks, wonder if we can get the assignment scheduled. I think I saw it somewhere for Christmas earlier, so that we can relax in the Christmas holiday. Yeah, so the assignment is going to involve specifying a probabilistic model. That means that we cannot schedule it very early, because you'll just lack the knowledge and skills to do that, to complete the assignment. It's also suboptimal to assign it after the Christmas break, because that just gives you not a lot of time. Then you'll be working on the assignment during your exam week, and that won't be well, I mean, it's not that drastic. It's something to talk about. Can you reset earlier? Well, like I said, if I release it earlier, then you don't know how to tackle it, essentially. I mean, I could probably release it mid-December. That should be fine. So for a bit of background information, the assignment is mostly complete, but I'm still thinking about. So Julia is a very friendly language, and it's really easy to get into if you're already familiar with MATLAB and Python. But every year we also have students who are not so familiar with MATLAB or Python, and Julia is really a threshold. And I'm thinking of ways of letting students complete the assignment without having to use Julia, and that there's some other that they can do it in some other programming language. Some people like Scala or C, or you also saw this connection to Lisp, for instance. And really, so throughout the course, we'll be using a probabilistic programming software package that our lab, the lab that Bert and I are in, develops, and it's a package that we know all the way through, and it's also well known, well positioned within the probabilistic programming community. But it is sort of Julia specific, and so if you let students work in a different programming language, then they will not be using that particular package, but they'll be using some other package. So, I mean, it's not without a learning curve. So if you decide to work on the assignment in a different programming language, you'll also have to familiarize yourself with a different software package that does probabilistic programming. So I'm still trying to think of a good way to handle this, to deal with this, but I guess it's just a matter of making a decision, and then I can release the assignment. I might do it mid-December, so not the final week before Christmas break, but probably not much sooner than that. Does that answer your question? I'll just move on to Heng Jiang.
Yeah, I just want to know, when will you gonna upload the assignment for this week?
There isn't an assignment this week. So
I saw that. I mean, in the end of the tutorial, and you said there will be like a practice one for us to have, and you upload it on Canvas.
Oh right, yeah. So the sorry. Sorry. Yeah, so we recorded the video lectures last year, and so we only got advance warning that this year the course will be online a week before the course started. So, I mean, there was no time to re-record all of the lectures. So we used the recordings. We're using the recordings from last year. Last year we did have separate probabilistic programming exercise assignments per probabilistic programming session. So you would get an additional notebook, and you would have to do something. And I designed these notebooks to be fixed somewhere, so it would generate some code. You could submit it to me. I run it through an auto grader, and then I post your result online. That's how we did it last year. There was some student feedback that these assignments were not, or I mean, could be improved in a number of ways. And then this year we decided to just have one somewhat larger assignment that combines all of the parts of the previous probabilistic programming assignments. So the YouTube lectures will say that there's an exercise or an assignment that has to be completed for every probabilistic programming session. So that's not the case. I'll see if I can cut that part from the YouTube lectures.
But can you still give that to us? Because I really want to use those more exercises, you know, to practice Julia, as I don't know this language before. I think this small exercise can help me a lot.
I can upload them to Canvas, but I mean, I built them last year using a different version of Julia and different versions of some of the dependencies. I mean, I can just post them, and you'll. I mean, you can try them out and see whether everything works nicely. But I mean, there's a chance that you'll open the notebook and you'll not be able to get some of the code running because it works on older versions of certain software packages. Still, I mean, you can have a look at what the what the questions look like, and yeah, if you would really like that.
I just think that maybe, yeah, because I'm really a beginner in this, and maybe some small exercise will help me know more about this.
Yeah. So Julia Lang also has some tutorials. If it's just about learning more about Julia, Julia also has yeah. Julia has a number of tutorials. Oh yeah, it's Julia Academy.
I also watched that 2 hours tutorials and other stuff. They saw some difference, and as well as this website, there's differences. But I really think that some small exercises can help me understand better of the context.
Yeah. Okay. Yeah. I'll discuss this with Bert, and then we'll post something on Piazza, I think, on whether we can provide something.
Oh, okay. Thank you.
Yep. Sveta?
Hi. So I just want to know if the assignment is a group project or a single submission.
No, it's a single submission.
Thank you.
Yep. So I'll talk a bit more about the probabilistic programming notebook. Just go through it briefly, and that'll give you a chance to, if you're suddenly reminded of, oh yeah, I had some questions about this part, just raise your hand or post something in the message. I can't see it on my laptop directly, but I can switch. I'll switch back and forth every once in a while. Yeah, so yeah, I think so. In this particular probabilistic programming session, it is important to play around with these three particular parts. So what does a likelihood function look like if you plug in data and if you try to vary a parameter? What does a prior distribution look like if you start playing around with these parameters of the distribution? So here you can just, if you've opened this notebook on your own machine, you can just here try different values for alpha and beta, and then see it warp in different shapes. Bert already showed this during his theory lecture. Here there's also a comparison between different shapes of this. The point of the great thing about a beta distribution is that it's extremely flexible. You can encode any kind of belief about this parameter theta. So some of the code notes here as well. So certain things are very similar. So you use for I is 1 to 10. That's like the same in MATLAB. Or for I in a list or a vector or something, that all works. And then one particular thing about Julia is that you have this explicit command to do things in place. That means that you have some data in memory and you're mutating that in place. You're not copying to a different variable and then you applying a transformation and then pulling it back or something. No, you're altering data in memory straight away, and that is one of the reasons why Julia is often, or as Bert already mentioned, Julia walks like Python, runs like C. Julia is really designed to be as intuitive and easy to get started with as Python. So you can just open a script and try a few codes. You don't have to write all this boilerplate code. But under the hood, it's also still it's a strong typed. It has all these pointers to memories. You can write very efficient code with Julia that runs very fast. Yeah, then there's this this point. So you might have this. You should really think, if you're familiar with MATLAB, you should think of this point as in MATLAB you'll have A times B, so capital A times capital B, that will form a matrix multiplication. But then you can also do A dot times, and they'll do an element by element multiplication. And that notation has been taken over by Julia, so you'll see this point not just on point asterisk for element by element multiplication, but you'll see this point on a lot of things. You'll see it on point equal equal. That means that it's going to check for every element in two vectors whether they are equal. Or you're going to see it here on likelihood point theta. That means it's going to compute the likelihood for every element in this vector theta. You'll see that a lot. It's very convenient notation. It's really something that's sort of been learned from MATLAB and Python, and it's now being it's very comfortable to work with this. Yeah, so the example that we're using in this first probabilistic programming session is again, like, we're trying to bridge this gap between theory and application. So we'll have a very concrete example of this beer tasting fair. This is something that actually happened in Amsterdam a couple of years ago. It's just on a Friday afternoon. It's a fun thing. I mean, I wasn't there, we weren't there, but it seems like they had a lot of fun. Well, where was I going with this? Yeah, but so this example still, I mean, you can see that so if you look at these equations, it very quickly gets very mathematical again. But you know, F and S are just the people who got it right, and F are the people who got it wrong. So try to keep in mind where those variables relate to. And theta is really about, do you think people are able to guess alcohol-free from alcoholic beer? And usually, if you ask someone on the street, do you think that the people are able to do this, then they'll give you a single value. Yeah, I think with probability 0.7, I think that 70% of people are able to correctly discriminate this. And then really the difference, or the thing that makes Bayesian inference, makes Bayesian inference different from other forms of or frequentist statistics, is that we aren't looking at specific values of theta. We aren't looking at, we think that 70% of people are able to correctly identify this. No, we were going to assign some probability to each possible value. So we think with probability here 1.25, we think that the 70% of the people are able to correctly distinguish this. But probably 1.5, we're able to think that 50% of the people are able to correctly distinguish this, and so on. It spans. So there's much more information here. We have a much richer, much more descriptive description of our state of belief. And we can always resort back to, we can always fall back to these particular statements. So if we take the maxima a posteriori, then we will say that, you know, we think that 70% of people are able to correctly distinguish alcoholic from alcohol-free beer. So we try to keep this much richer, much more descriptive, I'm doing a mathematical description of our state of belief. We try to keep this in our model as long as possible, and only when forced do we resort back to a single statement about a single value. So no further questions so far. Yeah, and so model evaluation. I saw some questions on Piazza already about model evidence. That's corresponds to this term. So you would take the joint distribution, integrate out theta, and that gives you the evidence term. It's a very difficult operation, but it does give you a number that says that there's this much evidence for this model. However, yeah, if someone tells you, I mean, there's 5 evidence for this model, that really doesn't tell you anything. And so only when you're comparing models does this really make sense. And so here in this particular part of model evaluation, you've also seen this in Bert's lectures, but you're comparing models. You're comparing evidences, well, in this case not evidence between models, but when you have this particular special case, this particular simplification that we can use to do a particular comparison between two models. And that's actually very, computationally very easy to do if we have these packages that encode parametric distributions, and given that we know these parametric functions or probability distributions, you can just call PDF. That's a one-liner function that you're evaluating, and you're getting a result saying that it's more than 200 times more likely that they are able to discriminate. Any questions on this part? Oh yeah, Heng Jian?
Yes, do I need to understand how you derive this? How to get the
Savage-Dickey ratio, or just the base vector? No, I don't think so. So in general, I try to keep the probabilistic programming sessions to not introduce new material. So we're just going to go over stuff that Bert explained, and we're just going to use it or reuse it in a different context to familiarize yourself with these things. Here I've used the Savage-Dickey ratio because it gives a convenient computation, and that gives you back a bit more intuition on okay, so what are base factors, what is model comparison. These are the kind of statements that you might get out of that.
Yeah.
But it's not necessary.
Okay, thanks.
So one way to, if you are having doubts about what part of the notebook is really exam material, note that everything that's written here is part of is material for the exam, but the derivation of base factors into the Savage-Dickey ratio is not shown here. So that derivation is not part of the exam material. That means we won't give you on the exam some description of hypotheses and then say derive the Savage-Dickey ratio for this. That's not going to be the case.
Okay, thanks.
Yep. Any further questions? If you're still having trouble with installing Jupyter and Julia, you can also stick around after we stop the recording, and then most people leave. Then you can I can try and help you get everything installed. So normally, if we teach on campus, then this is the way we do it. We just get people in class and say, we'll help you get everything started. And now, yeah, we have to do it remotely over Piazza and everything. And I understand it can be a bit frustrating sometimes. If you're trying out some things, you're getting some errors. You post it to Piazza, you're not getting any responses right away. We try to be fast. I, for instance, currently have for a few days now an internet outage at my home, so it's that prevents me from going to Piazza and outside of office hours. But I mean, we're trying to make this as we're trying to help you as fast as possible. I think most of the issues have been resolved. So if there's anyone who's tried to install Julia and Jupyter and hasn't succeeded yet, I do suggest trying as soon as possible. And if it fails, posting the error as soon as possible, then we can get you on the way. These probabilistic programming sessions last year were very much appreciated in trying to make the Bayesian machine learning a bit less abstract. Okay, if there's no further questions, no questions asked in the chat, then I think I'm going to stop this live class. Oh, so Con asked, how do I know which distribution to use? For instance, we use the beta distribution for the coin toss example, and how can I find the likelihood in the joint distribution in the model specification? Okay, so that's two questions. First, how do I know which distribution to use? So generally speaking, I mean, we'll get more into this throughout the course, but generally speaking, there are a few combinations of likelihood functions and prior distributions, which are very convenient, very easy to work with, because they allow for these wonderful simplifications that Bert has shown you, and it's also in this derivation in the Probabilistic Programming notebook. So if you take a likelihood function, that's this part, and if you take the prior, that's this part, you multiply them together, these exponents can be brought together. So things, they're of the form where you can apply such a simplification, and that gives you another something that has the same structure as a beta distribution. So here we're ignoring this normalization term, but that's I mean, there's a reason for so it's a bit more difficult, but in the end, if you understand this concept that there's a likelihood of certain form and there's a prior, and then they simplify and it gives us the same structure as the prior, that's just a very easy, convenient formulation, that also, I think, gives a very intuitive understanding of this idea of updating your belief about something. So don't get us wrong. It will take a while for you to really wrap your head around and really get used to this idea of thinking in terms of probability distributions for variables. So instead of thinking of, okay, it should be this value, or with all likelihood it should be that value, no, we're really maintaining probability distribution over all possible values, and it'll take some time to get used to that. And this idea of updating your belief after observing data helps with getting used to that idea. That you might see that over time you start out very uninformative. Every value of the distribution has equal probability, and then as you observe more and more data, this thing starts to concentrate around a few values. So that means that you are becoming more certain about that this particular variable should take values in a particular range. And so this idea of updating beliefs is very nicely shown mathematically in these types of simple models. It's called conjugacy. So certain likelihood functions. So this is for discrete cases. Certain likelihood function: Bernoulli, binomial, negative binomial, Poisson, categorical, multinomial. They have a particular prior distribution that is conjugate. So that means that this property of multiplying the likelihood with the prior will result in a functional form that's similar in structure to the prior. And so this Wikipedia page, conjugate prior, gives a very long list of, so these are the prior hyperparameters and these are the posterior hyperparameters. So you can see that, if I start with alpha and beta, then alpha will be updated to alpha plus the sum of x. Beta will be updated with n minus the sum of x. That's what's being shown in this particular example. We'll start with alpha minus 1, we'll get s plus alpha minus 1, and that s is the sum of x that you'll see here. So beta Bernoulli is really the easiest Bayesian model, and throughout the course we'll see a few more examples. You'll see the Dirichlet categorical, and then we'll also move to continuous distribution. So the Gaussian likelihood in univariate and multivariate form, because that's a very useful. And all the way at the end, we might also see gamma priors for variance parameters and precision parameters. But in general, you can. So if you're interested about what prior should I choose, you can check this list. Okay, if I have a likelihood that's listed here somewhere, then I might choose the conjugate prior that's listed on the right here that will make computation and everything easier, and it'll help you develop an intuitive understanding of the idea of belief updating. But as Bert also mentioned last live class, in theory you can use any probability distribution, just certain additional considerations will arise. For instance, if you use, so this theta parameter for the Bernoulli is supported between 0 and 1. So if you use a Gaussian as a prior, you'll need to consider that Gaussian will assign some non-zero probability to values of that parameter smaller than 0 or larger than 1. That has some effect on the posterior. Do you want to allow that, or do you want to truncate your Gaussian prior to a 0 probability between or outside of the 0-1 interval? That means you have to renormalize your truncated Gaussian. So that'll introduce some additional considerations, but it's not impossible. And your second question, how can I find the likelihood in the joint distribution in the model specification? Right, so here in this inference part, we've set up base rule. So we have P of D, the data set given theta, and then P of theta. And if I multiply those, I'll get a joint distribution. So that's exactly what's happening here. So, so P of D given theta times P of theta, that's the product of likelihoods of the individual observations, and then times the prior. So if your question is how can I find the likelihood in the joint distribution in the model specification, it's here. It's this product over theta xi times 1 minus theta 1 minus xi. This is the likelihood. You'll see more as we go through more models. You'll see so one of the other things to really get used to in Bayesian machine learning is that it's usually a good idea to write things down in terms of this P notation, the calculus of probability. So there's certain things you can do and certain things you can't do in writing things in P, and so that's basically just the sum rule and the product rule again. So when you're conditioning on a variable, then you multiply it with the margin of that variable that gives you the joint. So this conditioning bar will change in a comma, so that sort of stuff. But note sort of under the hood, if you choose a particular parameterization for P, then you're multiplying the functional probability density or probability mass functions of those variables. So that'll look like this. But that's a bit hairier, and I think it's good to get used to this this P notation where you're updating beliefs and you're applying base rule and relying just on the sum and product rule before you really dive into wrangling functional forms of PDFs. Okay, yeah. Does that answer both questions, Con? All right, cool. So if there's no further questions, then I'll stop the recording.